Hello, calculus students. Welcome to another online lesson. Today we'll be talking about calculating the probability of independent events and dependent events. Our goal is to be able to solve IB level problems, such as those in the homework involving independent and dependent events. A little recap to start things off. I'm sorry, actually, some new terms and notation to start things off. Independent events are those events where the occurrence of one event does not affect the occurrence of another. And I think most of the examples we've looked at thus far have focused on independent events. For example, rolling a die and flipping a coin. I could get a 3 on that die, and it's not going to have any impact on whether or not I get a heads or a tail on the coin. These are independent events. Things like whether or not it rains and whether or not I get a raise at work. Those would be independent events. They shouldn't theoretically have anything to do with each other. So if they're independent events, we say that the probability of A and B is equal to the probability of A times the probability of B. Now remember, P stands for probability in this, and it's sort of like that function notation. P is a number, so there is one number that represents the probability of A and B. And again, I find that one number by multiplying the probability of A times the probability of B. This rule can be extended for any number of independent events. For example, if I want to find the probability that A happens and B happens and C happens, sort of like one of the problems we've done where I get a heads on a penny, a tails on the nickel, and a 3 on the die, I would just multiply all those together, and I could then have a spinner and multiply the probability of getting the yellow on the spinner and all this. But you just keep multiplying things together. So that's our key here. So let's look at example of that. Oh, before we do that, this is where we'll just do a quick review again on some terms and notation. The probability, again, of E, as we just showed, that's the probability of that a number or an event E occurs. And the probability of it is one number. Again, that number can range between 0 and 1. If we get a number that's bigger than 1, it's not correct. If we get a number that's negative, also not correct. We talked about complementary events. Complementary events, again, are those events whose probability add up to 1. The probability of getting a 1 on a die versus not getting a 1 on a die. We show that with our prime symbol, and the following equations will help us find complementary events. Okay, now on with our independent events. A coin and a die are tossed simultaneously. Without using a diagram, which I know many of you will appreciate, determine the probability of the following: getting a head and a 3, a head and an even number, a tail and not a 6. So why don't you take a moment, pause the video, and see if you can work out these answers on your own. As we show the work here, the probability of a head would be 1 out of 2. There's 2 possible sides to a coin, and one of them is the one we want, a head. And then we take the probability of getting a 3 on a regular die. There's 6 sides on a regular die. We want to get a 3. Now, don't put the 3 over 6, because ask yourself, how many different sides show a 3? There's only one side of a regular die that shows a 3. So there's one side I want of the coin, one side of the die. I multiply those together, and I get 1 over 12. Again, probability is a range of numbers from 0 to 1. 1 means it will happen. 0 means it will not. Anything less than half is less likely to occur, and this would not be particularly likely to occur on one trial. Part B, a head and any even number. So for a head, once again, it's 1 out of 2. For any even number, well, on a die, you've got 6 sides, so the even numbers would be 2, 4, and 6, which is 3 sides out of the 6. And I multiply, and I get 3 out of 12. Now, of course, that can be reduced to 1/4, but you don't have to reduce. You can leave it just like that, and I'm going to do that. Finally, part C, a tail. Still, only one tail out of 2 sides, and not a 6. Not a 6. Well, that's the complementary events idea. And so there's only one of the 6 sides that is, and so if I take everything and subtract the one I don't want, that leaves 5 sides that are not a 6. sides, 1, 2, 3, 4, and 5. And if I multiply those together, I end up with 5/12 is the probability of getting a tail and not a 6. Now that's still less than half, but it's very close to half. So it's almost equally likely chance of happening and not happening. All right, example 2. We've got 2 students, Gabe and Michelle. Gabe attends school 95% of the time. Michelle attends school 85% of the time. Find the probability of the following. First and foremost, Michelle attends, but Gabe does not. So we're going to need to use Michelle's probability of attendance, which is 85%, not great. I'm going to write that as a decimal. I'll write it down here. So for part A, I've got Michelle's attendance, which is 0.85 or 0.85. And then I need to have Gabe not attend. Well, Gabe has much better attendance, 95%. Her probability of not attending would be her complement. So if you take the whole, which is 100%, and you subtract the 95%, that'll leave you with 5%, or we could write that as 0.05 as a decimal. And we're just going to go ahead and multiply these. Since they're already written in decimals, I'm going to reach for my calculator, and we get 0.0425. 0.0425. Now, they originally gave me percentages. I now have a decimal for my answer, so I'm going to convert that by moving my decimal place to make it 4.25%. All right, let's look at one more of these. Let's do part D. Neither student attends. Oops. So for part D, Gabe is not attending. Neither student is attending. So I need to write down her complement. Again, she attends 95% of the time, or 0.95. So the complement is 0.05. We just used that. And then Michelle is also not attending. So she attends 85% of the time. If we take the whole 100% and subtract the 85, we're left with 15% or 0.15. If we multiply those together, we get 0.0075, also known as 0.75%. So how likely is that to occur? Not very likely at all. It happens less than 1% of the time. They both don't attend. All right, so that's the idea of independent events. Where one thing does not affect the other, we simply multiply. Now for dependent events are events where the occurrence of one does affect the occurrence of the other event. 2 or more events are dependent if they're not independent. So that might be useful later on when we start using formulas for things. And again, if they're not independent, that means they must be dependent. Once again, you can see here on this formula, we're just going to multiply. We're going to multiply the probability of A times the probability of B, given that A has occurred. Now, what makes something dependent? Well, again, it's the case of what happened before affecting the second outcome. Let me show you an example of that. Here we have a box. This box contains 4 red, 3 blue, and 1 white marble. We're going to select 2 marbles at random. We're going to pull them out of the box, and we're not going to replace them. We're going to do this without replacement, meaning I take 1 marble out and I keep it. And then we're going to find the following probabilities. Now, why is probability going to be dependent in this case? Well, the way we normally find probability is we look at the total. So if I look at this first question, it says that both of the marbles that I pull out are going to be red. So what's the probability that my first marble is red? Well, there were 4 red marbles, but there were a grand total of 4 plus 3 plus 1, which is 8 marbles total. So my first marble is going to be 4 out of 8. Again, 4 red, the one I want, and 8 total. Okay, so let's say I take out that first marble. Now how many marbles are left? Well, I took 1 out, so there's only 7 marbles left now. Then I want to get another red one. Well, how many reds are left? Well, assuming I got that first one, which is what we're calculating the probability of, now there's only 3 red marbles left. Again, why 3? Because we took one out on the first pull. In order to get both red, you have to get a red one on the first one, and you get a red one on the second one. But there are only 3 out of the 7 left now. So we can multiply straight across. We get 12 out of 56. Again, that can reduce, but you don't need to. Now let's do both are blue. So there are 3 blues. Again, if we start over from scratch, 3 blues out of 8. So 3/8 would be my starting probability. Now I want them both to be blue. So I take out that blue marble. How many marbles are left? Well, 7 total because we've taken one out. And how many blue marbles are left? Well, again, I want to get both blue, so I must have gotten a blue on my first pull. So there's only 2 blues left. Multiply straight across. I get 6 out of 56. All right, that's the case of dependent probability or dependent events, because the probability of getting my second one, even though it's the same thing I want, in the first case I wanted both red, second case both blue, but the probabilities changed based on what happened beforehand. Well, that's going to be the case here as well. As I look at part C, it says the first one is going to be white. So originally we started with 8 marbles. 1 is white, so 1 out of 8. Times, now, the probability of blue, knowing that the first one I took out was white. So how many total marbles will we have if I pulled out a white one? Well, I pull out a white one, so we have 1 less marble. But how many blues are left? The only marble I've taken out is white, so I should still have all of my blues, which is 3. So in this case, the denominator changed, but the numerator did not, again, based on what had already happened. So 1 times 3 gives me 3. And 56, again, is our denominator. Now let's do neither is white. This is a complementary problem. So if neither is white, there was 1 white, so how many were not white? That means there's 7 others that were not white out of the total of 8. Once I take one of those non-white marbles, there's only 7 non-white marbles total and 6 non-white marbles left. I'm sorry, 7 marbles total and 6 non-white ones. Multiply straight across, I get 42 out of 56. And last but not least, both are white. What was the probability of getting 1 white marble? Well, it's 1 out of the total of 8 because there was only 1 white that we had to start with. Now for my second pull, I've pulled out a white marble, so there's 1 less total marble, only 7 marbles left. And how many of them are white? Well, I took out the only white ones, so 0. 0 divided by 7 is 0. 0 times anything is 0. And so that probability is 0. Now, what does that mean? Can that happen? 0 was a number on our scale. It's a possible probability, and it means there's no chance that will happen. If we think about this logically, there was only 1 white marble. How could you pull out 2 of them? You can't, and that's why it's a 0% chance of happening or a 0 probability. But we also can prove it here on the mathematics, which I just did. All right, we'll save our last example for class, and looking ahead here, a bunch of pages of homework, but I think you will find that this is relatively easy. I just want to give you a good variety. So page 577, 79, 83, and 85.